Hey everyone, in this video, let's take a look at question 208, implement trie on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, a trie, or a prefix tree, is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure, such as autocomplete and spell checker. We want to implement the trie class, where trie initializes the trie object. Insert will take in a word and insert it into our data structure. Then search will go ahead and return true if this word is part of our trie, part of our data structure. And starts with will again take in a prefix and return true if there is a previously inserted string word that has a prefix, and false otherwise. So what does this mean essentially? So let's take a look. Maybe we have the following words. So let's say we have the following words. We have the word cats, dog, cat, and then dot. A trie data structure might look something like this. And if you kind of think about it, we can represent this in terms of a tree, and they actually want us to because it's a tree data structure. And so maybe this over here, this is like one node, right? Maybe we can call this like a trie node or something. And so what do we notice? Well, a trie node has a value, right? You can see that all of these have values. This value is a C, this value is a D. What else does it have? Well, it has like children, right? It has like what it points to. It has like its left child, it has right child. But if you kind of think about it, instead of just left and right, we can have a maximum like 26 children, right? Because there's 26 alphabets, 26 letters in the alphabet. So for example, for cats over here, you can see here we kind of have like a root, which is like this node over here. Then we have C, actually the root child, which is a C here, a C node, and that has a child for A, and then we go to a T, and then we go to an S. You can see similarly, we also have cat, right? Cat is just this, and then C-A-T. We also have dog and dot. Notice that for dog and dot, after the O over here, we actually have two children, right? We have one for the G and one for the T. And so our insert function will essentially take in a word and insert it into our data structure here. Our search should somehow go through this tree and return true if we have a word, right? So maybe, let's say I search for the word cat, then I should actually return true here because cat is part of the word. And then starts with is basically just going to return true if there is a string that we can form in the trie such that it matches the prefix. So for example, maybe I have just the prefix of D, or maybe like DO. You can see that we can form like a continuous string here, and so we would return true in that case. But for something like DOA, well, there's no A over here, right? There's no A child over here, so we can't really form that. So we will return false there. So there's many different ways to do this, right? There's one way in which like we actually create the individual nodes here. So you would have like a actual class over here for the nodes, and then the class would have like maybe something like a class like node, and then the class would have like a value and like like array of children. So this is one way, but this is actually not the way that I want to do this. In Python, it actually becomes very simple because if you think about it, a node, we can kind of represent this in terms of a dictionary, right? So what do I kind of mean by that? Well, let's say over here, like this initial root over here, we can say root is just like an empty dictionary, something like this, right? And let's say I want to insert the word cat. Okay, so what would I do? Well, this dictionary over here is going to essentially contain all of my children, if you think of it that way. So right now I have no children. So right now I just have this one root here. I have no children. And then when I insert a C, what am I going to have? Well, when I insert a C, then I can have something like this. I can have that my dictionary becomes C, and C in itself actually is its own dictionary. So you can think of C in itself as something like this. So maybe there's other keys over here, but C in itself is this entire thing here. And so if you think about a C, C's child is this one over here, the A over here. So really what this would kind of look like is if I go ahead and remove this, it would kind of look something like this. So we would have from the root, we would have a child C, and then C would also be a dictionary, which has its own children. Here we have a children of A, and then A is its own dictionary, which has a child of T, and then T is its own dictionary, which has a child of S, and then S actually doesn't have any children at all. And so you can kind of think of it like this. So we're doing the same thing, but we're just representing it in terms of a dictionary. We're not creating new nodes over here. And so you can actually imagine here, right? So maybe instead of just the A, you can see that the root here also has like a D, right? So here we would have like D also points to its own child over here, and then D points to like a O, which points to a G and a T, etc. So hopefully you're understanding the point here that I'm trying to make, but essentially we can represent this in terms of a dictionary instead of a node. And so doing that actually simplifies our approach quite a bit. And so there's just two more questions to answer, right? How do I know whether I have like a word, like I can search for a word. And how do I know that I start with a word? Well, let's start with the starts with first, right? So if I ask you like, you know, do I have like maybe starts with CA? Well, or maybe all I really need to do is like I just need to go through the string, right? And then I need to check, okay, does C exist? Okay, C does exist. Now I'm going to look for the A. Is there an A inside the children of C? Yes, there is. So we can conclude that this is a valid like prefix. If there isn't, if it was something like C and then D, for example, well, in this case, like it wouldn't work, right? Actually, I realized I put D over here. So D should not be here. So actually, if I was to kind of draw this entire thing again, what it would kind of be like would C would point to A, would point to T, would point to S, and all of these would have like their own children like this. But in addition to this, we would also have like D here, and then D would point to O, would point to G, and then also point to T, etc. So that's like another way. This is the better way of representing it. So basically, if we're looking for something like CA, I can check if like CA is a string. And in this case, I can see that it is. So that answers that question. The next question is, and I guess the final one is like, how do we realize a search, right? Like, how do I know that a string exists inside of the search? And I can't just follow the same approach here, right? Because, for example, if you put like CA, well, CA definitely exists, but the string doesn't end here, right? The string actually goes to CAT and actually CATS. And so the way we want to do this is like, we want one way to like figure out that, you know, this is like the end of a word, right? And really, if you maybe think of it in terms of a node, maybe we can have something like end, and then this would be like a Boolean, right? So this would either be like true and false, indicating that at this node, a string has completed. And so we can actually do the same thing over here. Essentially what we could do is maybe every time a string completes, we can add like end as true over here. So end as true. And so what this would kind of look like, if you think about it, is if we had this entire thing here. So let's take a look. If we had this entire thing here, I'm going to skip over the D, just look at the C, and then just look at the A, and then just look at the T. So T will have its own children, and then like, you know, there can be more things over here. But as part of the children, maybe we can have something like end, and then we set it equal to true. We know that the child will only be like one letter at a time, right? So we're completely allowed to add this. But we can notice here that the CAT over here, if we have this scenario, then this is a true case. Like this is a case in which a word ends. So let's take a look at how we can do this in the code to better understand. And so it's actually completely very simple on how we do this, especially in Python. So let's take a look. So first thing we need is we need like our root, right? And I think I'll just call this children. So I'll call this children, and it needs to be a dictionary. And I'm using self because I need to refer to it everywhere. So first thing I can do for insert, let's start off with insert. I can do C is equal to self.children. And then when I'm inserting, what do I need to do? Well, if my word is something like bat, for example, then I need to go through each letter. So for W in word, then I need to essentially create like the nodes, which in this case is the dictionary, right? So I can actually check. I can check that if W not in C, then C at W is equal to an empty dictionary. So all this is doing is that if like initially when we have an empty dictionary, this one we can see that we don't have like a B here. So we're going to create a child B, and that will also have like its own children. So what this is essentially doing is like from this node over here, if you think about it from this node, all it's doing is that it's creating like a B over here for the bat. That's what it's doing. And then what I'm doing, so if this is not the case, then what do I want to do? Well, now I want to move forward, right? Now I want to consider the A over here. But in order for me to consider the A, I need to essentially move like my C variable here into the B's children, if you think about it, right? So I can do C is equal to C at W. And so what this will essentially do is C will initially start off over here. So this is like our pointer to the root. And now my root pointer will be over here. And so I can look inside of like B's children to see if there's an A or whatever. We can see in this case, there's not going to be anything. So this will continue to loop. And then at the very end, what's going to happen? At the very end, we'll have our T, and then C will be like T's child, right? So it would be something like this. So we'll have B, and then we'll have an A over here, and then we will have a T over here. And now C will be on like T's children, which there are none, right? So C will be like this empty dictionary here. So what I can do now is actually, once this completes, I can do something like C at end is equal to true. So all I'm doing here is I'm just saying that, okay, one of the children, let me have the value here set to end, and I'll just make it equal to true. So that's all I'm doing over here. Okay, so if you think of it in terms of that, that's all we really need to do here. And then search becomes very easy because all you need to do in search is, again, we'll go through the children. And so we'll go through the word itself. And then if we can actually check this, right? So if we can check actually, if W not in C, then automatically we can return false, right? Because we know we're missing a letter. But if it is, then we're going to keep going till the end, right? And then what I want to do is I want to return end in C. Because if you think about it, maybe I enter the word like CA, right? Well, CA definitely exists, but you can see there isn't an end over here. There isn't an end. The end only exists as CAT and CATS. And so that's why we have this scenario here. And then the starts with is actually even easier than that. All we have to do is, again, we'll look at the children. And then, again, we'll go through the prefix. And so I can actually, again, just check. If W not in C, then I know that this prefix is not valid, right? So then I can return false. And then otherwise, I will just advance my pointer again. And then in the end, I can just return true, right? Because I know that I haven't returned false so far. So in the end, I'm going to be on any one of the children. I might be on the C, I might be on the A, I might be on the T or the S. But I know that this is a valid prefix. So this is all there is to this question. And so if we go ahead and run it, we can see that it works. This is the O of N type algorithm where the insert and the read and all of the operations are O of N. And so you can think of this as like a very easy approach to solve this question. Thanks for watching.